Okay, good morning once again to all the students. We'll complete our 13th lecture, which we have left in the middle due to lack of time yesterday, and then we'll move on to our 14th one. So in yesterday's class, we started learning about what is reinforcement learning. Reinforcement learning will have an agent in an environment, and that agent takes steps in order to move from one state to another state, takes actions in order to move from one state to another state. Say the set of states are represented by S and the set of actions are represented by A, then whenever it takes an action to move from a state S1 to S2, then it will be given a reward denoted by small r, lowercase r. Okay, this reward mentions whether that action taken is appropriate for that particular step or not. So the agent's ultimate goal is to reap all the rewards and increase or maximize the accumulation of such rewards in order to get maximum cumulative reward, and it should minimize the penalties. Okay, so every action taken by the agent in the environment should be appropriate, and it should be according to a control policy which will help to maximize the rewards accumulated by the agent. Okay, this is the introduction we got in yesterday's class, and for that we understood that concept more deeply using this diagram. In this, in the environment, the agent will move from one state to another state by taking a specific action appropriate for that state, optimal for that state. Why we say optimal is only optimal actions will be rewarded. Non-optimal actions will not be rewarded. Sometimes they will be penalized also, so that it will reduce the number of accumulated rewards or the sum of accumulated rewards. Okay, so the action should be taken appropriately. The action that is taken from a current state S should be optimal so that it receives rewards from the environment. The environment can directly give the reward or feedback, or it can contain a trainer or a teacher who can give indirect feedback to the agent in terms of rewards. Okay, and that is also represented like this, like a sequential pipe. An agent can start from move from state S0 to S1 by taking an action A0 and receiving a reward R0. In this case, we assumed R0 as a delayed reward. Why? Because reward for an action taken by the agent to move from one state to another state is not known until that action is taken. Right? That is why it is called as delayed reward. And also we understood that agent will be interested only in immediate rewards in the learning process rather than delayed rewards. That is why we took a factor or a constant gamma which lies between 0 and 1. This gamma is a discounting factor. It indicates the time that is taken to give the reward to the agent. If the time is more to give the reward to the agent, means if the delay in giving the reward or feedback to the agent is more, then that reward's importance will be reduced in the learning process. So immediate rewards are always appreciated. So gamma has to be kept as low as possible towards 0, indicating that there is not much delay in giving the rewards to the agent in the learning task. And we also understood the difference between function approximation and reinforcement learning. In function approximation, a training set is given and a linear equation is built, or a polynomial equation is built. Or some equation is fit according to the behavior of that data, right? So a function is approximated in order to almost explain the behavior of the data. Approximation is just an estimation, okay? It is not 100% representation of the behavior of data. That is why we call it as function approximation. Now, what is the difference between this reinforcement learning and function approximation, which we have seen in linear regression? Delayed reward. There is no such concept as rewards in function approximation, but their errors can be calculated. Once the prediction is made, what is the difference between the existing value and the predicted value can be measured, and mean of squared errors can be taken, and that has to be minimized as much as possible in order to get an ideal function approximation, to get an ideal target function. But in reinforcement learning, we have some concept as reward, and that reward is not a immediate reward. It is delayed reward, not a prior reward, not immediate, not a prior reward. It is a delayed reward. Only after some action is taken, then the reward will be given by the environment in order to know the agent whether it has taken an optimal step or not, whether it has performed some optimal action or not, to move from one state to another state. And other difference is exploration. In this case, in reinforcement learning case, we have two choices. One is exploration and the other one is exploitation. Exploration means if the agent can take some decisions by exploring its previous values, by exploiting its previous learned values, then it is called as exploitation, learning by exploitation. It is referring to the previous knowledge of the agent in order to learn to take an important step in future. But sometimes it may prefer to explore unknown states and actions. Instead of referring to its previous knowledge, it will sometime become ready to take a new step. That is, explore a new step. Okay, for this particular state, what action I have to take? For this state, there are well-proven actions in the history, but the agent doesn't take help of them. It will try to explore a new step because sometimes it may be better than the existing steps. Then why stick to the existing steps? Sometimes it will decide, say, if the cost of exploring is much lesser than the cost of exploitation, that is referring to existing knowledge. In such cases, it can take risk of exploring unknown states and actions. But that kind of experience is not available in function approximation. It has to stick to a static data set in order to approximate the target function. Now, partially observable states is also a feature of this reinforcement learning. Means all the states can be observed completely. And for that, we have seen an example of camera which can capture motion or video only in the front side. Then what about the back side? For that, getting complete experience of the entire environment, it should have to use knowledge that it has got in its previous scenarios about the other parts of the environment also. Okay, so most of the time the observable states are partial, and in order to get a complete view of the environment, it may have to use its previous knowledge. Right? In such cases, we call it as partially observable state. Partially observable states. And if at all it has to enhance its actions, then it can improve on observability of the environment itself. Only if it increases its chances of observing the environment completely, that will add up to the performance of this agent in that given environment. And finally, lifelong learning. It is not that you train the machine learning model once and use it for all kinds of purposes. It is not like that. In other supervised and unsupervised machine learning models, you give a training set, you give training examples, and the model learns from those training examples and creates an ideal target function, or formulate some hypothesis in order to explain the behavior of the data, but that is not the end in reinforcement learning. That is not the case in reinforcement learning. It learns lifelong. It has to learn whenever it encounters some new environment. For that, I have given you an example of autonomous driving vehicle, which learned driving on state highways and national highways. But when it has to learn driving on hilly slopes, it doesn't give up, right? It starts learning again. In that kind of driving environment, in what way it has to drive on the hill turnings, pin curves, U-turns, or sharp bends. In such cases, how to learn driving on that slopey areas by using its experience that it has derived by driving on highways and state highways and national highways. Okay, so the knowledge of driving is used in this new learning process in order to learn how to drive on hilly areas. Okay, that is called as lifelong learning, which is an inherent feature of reinforcement learning. You can't make any machine stop learning. It has to learn, it has to continue with its process of learning whenever it comes across a new kind of environment, right? And also we have seen how the learning task can be formulated by using a Markov decision process. Markov decision process states that a system is dependent on its immediately previous state. Means the current state of the system is dependent only on its immediately previous state, not on all its previous states. Okay, so that is called as Markov decision process. For that, when the machine is learning a policy, control policy, optimal control policy, or let us first treat it as control policy, then we'll go for optimal control policy, 5-star. Okay, so when the task of the agent is to learn a policy pi such that it maps from set of states to set of actions, means from which state it has to take an action to move to the next state. Okay, that mapping. For all set of states, what are the possible actions that can be taken to move to the next state? That is the control policy that has to be learned. For selecting its next action AT based on the current observed state ST. What is this T? It tells us about the point of time at which that particular state of the agent is captured. Okay, so we denote it by AT and ST. Now, if an action has to be defined, that action AT is defined as pi of ST. It is a function of the state. An action can be taken as a function of the state because from that particular state, say in a game, a board state, you can take only specific kinds of actions. Other kinds of actions may be illegal moves in that board state. Right? So pi of ST will determine what action can be taken from that particular state ST. Okay. Now, how shall we specify precisely which policy pi we would like the agent to learn? Obviously, it is the greatest possible cumulative reward for the robot over time. Robot or any learning system over time. What would be the optimal control policy? What would be the appropriate control policy? The policy which will make the agent to increase or get the greatest possible cumulative reward. It should not at all be penalized. It should get maximum possible rewards only. That is the best control policy. That is the set of moving sequences. Sequence of moves. That is the set of sequence of moves a particular robot can take in order to reach its final destination or perform its particular task. Okay. For that, we have indicated V pi, that is the value of rewards that can be accumulated. The value of rewards that can be accumulated by following a control policy pi to move from a particular state S at time t. It seems to be a simple notation, but I'm reading it for nearly 20 seconds, right? The value V, I'm reading it again, the value V cumulate, which is the value of cumulative rewards that can be accumulated or collected by following the control policy pi to move from state S at time t is how it can be represented is, it is the immediate reward given at time t, RT, plus gamma RT plus 1. See, when the time factor is moving to the next, what to say, slide or next slice of time. Say the immediate slice of time is t. The next slice of time is t plus 1. So when the time is delayed, then discounting factor comes into picture, that is gamma. Gamma will indicate the decline in the importance of that reward as the time is delayed to give that reward. Okay, so it is gamma r t plus 1 plus as the time slices increases t plus 2. Even the discounting factor also increases exponentially, means the reward that is delayed too far will lose its importance exponentially. That is being mentioned here. So how is this mathematically represented, this entire line? It is nothing but the sum of products of the discounting factor, which is increased with respect to time slices, multiplied by the reward given at that time slice, t plus I. Okay, that is the value that can be accumulated by following the control policy pi to move from a state S at a time point t. Right, this is how we represent it. And I have given explanation for all this. Let us go to the illustration directly so that I think you will be able to recollect what you have learned. To illustrate these concepts of learning tasks, a simple grid world environment is depicted in the topmost diagram of the figure. See, this entire thing is called as grid world environment. Why? Because the environment is depicted in the form of grids, okay, for a particular agent. Now observe carefully. All this explanation I have given in the upcoming slides, but let us first understand the basic idea behind this diagram. Now, this entire box explains about various states of the agent. Okay, so this R of SA will indicate the reward that can be given to the agent when it moves from a state S by taking an action A. Got it, students? Is it clear? This box indicates, this grid indicates the environment in which an agent is taking some actions to move from one state to another state. So R of SA indicates the reward given for moving from state S by performing an action A. If it is an appropriate action, it will be given a positive score. If it is not an appropriate action, it will be given a negative score. Okay, so let us take, it is starting from here. If it moves in either direction, the reward is 0. Why? Because it is not moving towards this goal state. Observe this G box is called as the goal state. So everywhere else, in whichever state is the agent, when it moves to the other state, the reward given is 0, except when it is moving to the goal state. That is why, see, this reward R of SA is given as 100 because from this state, it is moving towards the goal state. And when the agent is in this particular state, if it is moving towards the goal state, it is given the reward 100. Everywhere else, did you notice the reward value is 0? Why? Because entering into some other state, which is not a goal state, is not a rewardable action. It's not an anticipated action. It's not a desired action. That is why it is given 0. Except when the agent is moving to the goal state. There it is given, the reward is given as 100. Now observe this Q of SA. This is the Q function that we are making the agent to learn. What is this Q function? This Q function will have a mathematical representation through which you can calculate the values of this Q in each state. Now, if you notice, when the agent is moving towards the goal state, the reward values are 100. But whenever it is moving away from the goal state, the rewards are reduced. But whenever it is moving towards the goal state, so that in its next step it reaches its goal, in such cases the reward is higher. But if it is moving away from the goal state, the reward is lower. Did you understand? That is decided by the discounting factor gamma. I'll show you how it is calculated. You just understand that when the agent is taking steps towards its goal, all those constructive steps towards reaching its goal are given positive values. And when it is moving away from its goal, it is given negative points. Common sense also, right? You need not know any formula for this. But how exactly that reward is calculated, that I'll show you. But basic idea is, if the agent is moving towards the goal, it is rewarded, and moving away from the goal, it is penalized. And this last state is called as the absorbing state. Why we call it as absorbing state? Because it is the final goal, because it is the final objective of the agent to reach this particular state G. Thereafter, it remains there infinitely. Means until some other action is assigned to it. In that case, it will be moving within the same place, means it stays, actually it infinitely stays in the same place. That is why when it is staying in the same place, the reward given is simply 0. Okay, once it is moving towards the goal, the reward given is 100, but as it remains in the same position until unless another task is assigned to it, the reward assigned to it is 0 if it continues in the same position. That is why this G is called as absorbing state. From this state, the robot no longer moves to other states because that is the required goal. That is why we call it as absorbing state. Okay. Now here you can see the rewards accumulated. Rewards accumulated when moving from one state to another state. Here, what is the reward? If a robo moves from this state to this state, the reward that can be accumulated is actually not a reward, it is a penalty, because it is reducing 9 points here. But once it moves in this direction, it is moving towards the goal. So some marks are added here, 9 points are added here, which becomes 90 again. Now it is further moving towards this position, which makes its next state to be the goal state. So the reward given, that is the appropriate step actually, optimal step. That is why the reward given here is 0, means moving from this state will give it a reward 0. Moving from this state will give it a reward 90. Moving from this state will give a reward 81. Moving from this state to this state will give a reward 90. Moving from 90 to this state, it will give a reward of 100 because it is nearing the goal. And once it moves to the goal, what would be the reward? It will be absorbed there. The agent will reach its final goal. So no more rewards will be given as the agent stays there until another task is assigned. So the reward that can be accumulated in that particular goal state is 0. Okay, did you understand this grid now? So how you can represent the optimal steps in arrows in this case? Just from this position, moving further, moving towards G can be done by following these arrows. That is the optimal step. Or if it is in this position, it can move from these grids in order to reach the final goal. Okay, these are the optimal steps. Now same what I have explained is given here in the slides. I'll just read out, try to recollect by keeping that figure in mind. The 6 grid squares in the diagram represent 6 possible states or locations for the agent. Okay, so agent can be in any of these grids. Now, when it is in any of that grids, what would be its optimal action to move to the next state? So that its final goal is reaching the final grid by accumulating the rewards, not getting any penalty. In order to avoid penalties, in order to get only rewards, it should take optimal steps at each say sequence, at each move, right? It should take optimal steps at each move in order to get only rewards, maximize its rewards, and don't get the penalties. Okay, so each arrow in the diagram represents a possible action the agent can take to move from one state to another. Now, the number associated with each arrow represents the immediate reward R of SA. That is the reward given when moving from state S by taking an action A. The agent receives if it the reward that the agent receives if it executes a corresponding state action transition. Okay, so R is the reward it gets when it executes the state action transition. By taking this action, it moves from this current state S. That is called as state action transition. Now note the immediate reward in this particular environment is defined to be 0 for all state action transitions except for those leading to the state labeled G. That is what we have seen, right? In this state, in this state, in this state, everywhere the rewards that can be given for the action is 0, except when it is reaching its final goal state. Now, it is convenient to think of the state G as the goal state because the only way the agent can receive reward in this case is by entering that particular state. Now note in this particular environment, the only action available to the agent once it enters the state G is to remain in this state. That is why we call that G as absorbing state. Now, once the states, actions, and immediate rewards are defined, and once we choose a value for the discount factor gamma, remember you can choose the discount factor here, which lies between 0 and 1. Okay, if you keep the discount factor minimum, then you are giving more importance to immediate rewards. But if you take gamma to be maximum nearing to 1, then you are giving more importance to delayed rewards. But in any reinforcement learning task, always immediate rewards are more appreciated than delayed rewards. Okay, that is why we try to sometimes keep gamma as less as possible. Now, once the states, actions, and immediate rewards are defined, and once we choose a value for the discount factor gamma, we can determine the optimal policy pi star. Control policy is indicated by pi, and optimal control policy is indicated by pi star. And its value function V star of S means by following this control policy pi star, how much rewards can be accumulated V star. Okay, that is denoted by V star of S. In this case, let us choose gamma as delayed reward only, highly delayed reward, that is 0.9. Let us see how it works. Now the diagram at the bottom of the figure shows one control policy for this setting. Like any policy, this policy specifies exactly one action that the agent will select in any given state. Now see here, this is how these rewards are calculated. Now from this position, see I'm highlighting this from this position, if it is moving further, means if it is moving towards the goal, in that case, it is given 9 points, means 9 into 10. It is moving, 0.9 into 100. It is moving towards the goal. Okay, so it is given 90 points. But when it is moving away from the goal, that 9 points will be reduced. That gamma factor is accordingly reduced, which will give the reward value as 81 instead of 90. Okay, that is how all these rewards in the grid are calculated by taking the delayed gamma value as 0.1, the discounting factor as 0.1. Now the optimal policy directs the agent along the shortest path towards the state G. Okay, the agent tends to reach the goal, but what is the use if it takes a longer path? That is why the rewards will guide the agent in a proper direction in order to reach its goal. So if it takes an optimal step, immediately it is rewarded. So it knows that that is the optimal step. Then it takes another step forward. If it is penalized, then immediately it will know that it is the wrong step and changes its direction. That is how control policy is learned by the agent. Now the diagram at the right of the figure shows the values of V star for each state. For example, consider the bottom right state in the diagram. This state will indicate the maximum number of rewards that can be accumulated, that is V star of S. Now moving from this particular state to the next state, it can accumulate reward points 90. But moving from this state to the next state, it will accumulate reward points 100. Why? Because that is the final goal state. That is how V star values are calculated. Now the value of V star for this state, that is bottom right state, what I have shown is 100, because the optimal policy in this state selects the move up action that receives immediate reward of 100. Now thereafter, the agent will remain in the absorbing state and receives no further rewards. That is why G state you saw an arrow like this indicating 0, because it remains there infinitely until some action is until some task is assigned to it. That is why the reward given to it is 0. Thereafter, that is what I am giving here in this point. Thereafter, the agent will remain in the absorbing state and receives no further rewards. Now similarly, the value of V star for the bottom center state is 90. We have seen that already, right? See, for this bottom center state, it is 90. Why? Because when from this state, it is moving to this state, it is actually moving away from the goal. That is why the reward points are reduced. It is given 90. But if it is moving again in this direction towards the goal, it can now it can accumulate the reward as 100 because it has taken an optimal step. Further, it goes to the goal state, and from this state, it can't accumulate any rewards because that is the final state and the absorbing state. That is why the rewards that can be accumulated here is just 0. Okay, this is because the optimal policy will move the agent from this state to the right, that is from the center state to the right, generating an immediate reward of 0, then upwards, generating an immediate reward of 100. So when it is moving towards the goal state, it will be rewarded with points 100. Okay, thus the discounted future reward for the bottom center state. What is the bottom center state? 90, right? So how is that calculated? It is calculated as immediate reward is 0, delayed reward that is given is gamma, and this gamma is the discounting factor, and that discounting factor we have taken as 0.9. So 0.9 into 100, you will get 90 plus, then no more rewards are given for later actions, for delayed actions. So this is 0 and this is 0, which will calculate the center state's value as, reward value as 90. That is how the values for each of the grid positions, that is the states the agent can be, is calculated. Now recall that V star is defined to be the sum of discounted future rewards over the infinite future. Why we are calling it as infinite future? It can learn endlessly from the current states in which all directions it can move. And once it reaches the goal state, it is infinite. It infinitely stays there until another task is given to it, right? In this particular environment, once the agent reaches the absorbing state G, its infinite future will consist of remaining in this state, that is why we call it as infinite future, and receiving rewards of 0. That is why here it is 0, here it is 0, and so on. So finally, the reward calculated for that particular bottom center state is 90. You understood now how that is calculated? 100 is the immediate reward because it is moving towards the goal. Gamma is taken as 0.9. That is why you got the reward for that particular state as 90. Moving into that state will give a reward 90 to the agent. Okay. Now we'll move to our 14th lecture. We have still 20 minutes time. What happens, Buddhi? Okay. In this lecture, we'll cover the Q function, simple algorithm it is. And this is important question also. They may ask you how to, they may ask you to write the steps of Q learning algorithm. Okay. So just pay some interest to it. So we'll first learn what is Q function and what is the algorithm for learning this Q function. This is simple session. We'll complete it quickly. Just focus. How can an agent learn an optimal policy pi star from an arbitrary environment? Arbitrary environment means an agent behaves only on the circumstances it faces, and that circumstances are not the same. Do you expect a robot to to drive a car always on an empty road? No. The real life situation is dynamic. It is arbitrary, right? Sometimes the traffic may be very high. Sometimes the traffic may be low. Sometimes the road may be completely empty. In all these arbitrary environments, the agent have to learn its optimal control policies according to which it has to act and take appropriate actions in order to move from one state to another state, right? So it is difficult to learn the function pi star, that is the optimal control policy, from set of states to set of actions directly, because the available training data does not provide training examples of the form SA. Do you have training examples like in supervised learning? In supervised learning, you have set of attributes and its target label. Then temperature condition, climatic conditions of the day, and whether a person will play tennis on that day or not, yes or no. You have set of attributes of climatic conditions and the final decision of a person to play tennis on that day or not. That is traditional representation of a data set, of a training set, but that is not the case in reinforcement learning. You will not have any training examples in the form of states and actions. Instead, the only training information that is available is the sequence of immediate rewards. If from this state, if this action is taken, what reward can be expected? Only that information is available. Okay, that is our SI, AI for every state and every action from 0 to and so on. Okay, so given this kind of training information, it is easier to learn a numerical evaluation function. So what if this kind of training examples are given to us, if this kind of reward values are given to us, then it is actually easy to learn a numerical evaluation function, the appropriate function using which we can calculate the the control policy, which we can frame the control policy based on this numerical evaluation. Okay, so given this kind of training information in the terms of rewards, it is easier to learn a numerical evaluation function defined over states and actions, then implement the optimal policy in terms of this evaluation function. How optimal policy can be implemented? Only by taking reward giving steps, reward giving actions, and avoiding penalizing actions. Now, what evaluation function should the agent attempt to learn? One obvious choice is calculating V star. What is V star? The value of the rewards accumulated. We are representing that with V star. And why initially we call it as V, but why V star? V star is the value of rewards accumulated by following a control policy pi star, optimal control policy pi star. Okay, that is one way to calculate the evaluation function. Now the agent should prefer state S1 over state S2 whenever the accumulated rewards with state S1 is greater than state S2. Say the agent is starting from state S1 and reaching its final goal. For that, say there are 100 points accumulated, 100 reward points accumulated. Now the agent is also in another case, it is starting from S2 and it is reaching the goal state, but it is accumulating only rewards 90. In that case, which one do you select? Which state do you select the agent to start from? Obviously, this state S1, right? We prefer the state S1 for the agent to start with, because if the agent starts from that state, it is accumulating more rewards. Okay, so the agent's policy must choose among actions, not among states. But actually, the agent's policy must be to choose among actions, because say agent is starting from state S1, agent is starting from state S2, agent is starting from state S3. But remember, the selection of the initial state doesn't decide the intermediate steps. Intermediate steps can be any. Though the initial state is not correct, intermediate steps can be optimized to get maximum rewards. Though the initial state is correct, because the intermediate steps are not optimal, it can get less rewards. How do you understand this case? That is why the agent's policy must choose among actions, not among states. It can use this V star in certain settings to choose among actions as well, not only the states. Okay, that is how we translated our problem. Initially, we thought states would help us to choose the evaluation function, but the intermediate states may be different. Intermediate steps may be different. That is why better choose among actions, that is the optimal action that it can take to reach the goal, rather than states to start with. Okay, so the optimal action in state S is the action A that maximizes the sum of immediate rewards R of SA plus the value V star of the immediate successor state discounted by gamma. What do we mean by this? Whenever you want to whenever you want to find the optimal action so that it moves from state S by taking an action A, that should maximize what the sum of immediate rewards, cumulative rewards should be more, plus the value V star of the immediate successor state. Okay, in that immediate successor state, in its next state, already there might have been some accumulated rewards, right, which are saved for that particular state in order to reach its final state. That V star can be taken, discounted by gamma. That is the discounting factor. So how can you represent that mathematically? The optimal control policy pi star to move from a board state or to move from a robot state, from one state to another state, what would be the optimal control policy? It is nothing but maximizing what? The sum of rewards for moving from that state by taking action A plus its immediate next state's cumulative reward values. There might have been calculated reward values for that next state, right? That cumulative reward values of that next state, delta represents change from state S1 to S2. Okay, so here we are taking delta, which indicates some change has happened in the state. Okay, so the rewards, cumulative rewards at that new state S for taking an action A might have been already available. Multiplied with the discount factor, that is the delay in calculating this reward, plus the immediate reward that is given. When you maximize this sum for taking the action A, that is the best move. Okay, so when you're moving from this state to this state, already there is some cumulative rewards in this particular state. Means because of entering into this state, what is the benefit? It is already stored there. That score is already stored there. Now, what is the reward for moving from this state to this state, and the cumulative value of rewards already in this state, adding both of them will give you the, and maximizing that will give you the optimal control policy. Got it? So the agent can acquire the optimal policy by learning V star, provided it has perfect knowledge of immediate reward R and the state transition delta. But in most of the cases, these two values are not a priori available. A priori means beforehand they are not available. What if the immediate reward R and the immediate successor delta are not known before the action is taken? What is the solution in such situations? Then learning V star will be of no use, because we don't know R, we don't know delta. Then what is the use of calculating cumulative rewards value? It is of no use for selecting optimal actions, because the agent can't evaluate this equation. When it can't evaluate the equation, it can't calculate the control, it can't design the control policy. It doesn't know what sequence of actions have to be taken. In that case, we have a solution, that is the evaluation function Q. So this entire introduction is given to you because to highlight the importance of Q function. What evaluation function should the agent use in this more general setting? When the immediate rewards are not known, when the cumulative value of the next state is not known, then what is the solution? You have to learn the evaluation function Q. Okay, this will provide us the solution. Q learning algorithm will provide us the solution. Now let us define the evaluation function Q of SA, that is the evaluation function Q, which is calculated at a current state A, and what action it can take from that state, so that its value is the maximum discounted cumulative reward that can be achieved starting from state S and applying the action A as the first action. Now, in other words, the value of Q is the reward received immediately. Q is the reward which can be received immediately by taking an action from a particular state. Upon executing action A from state S, plus the value, that is the discounting factor, delay in the rewards of following, plus the value of following the optimal policy. So what is the optimal policy here? How you can define the optimal policy? You can define it as a function of Q. Q of SA, that is the optimal evaluation function of moving from state by taking an action A, is equivalent to the immediate reward plus discounting factor multiplied by the cumulative reward value at the next state. Add both of them, that will be treated as your evaluation function Q. Okay, the reward that can be taken, this is known for the first step, right? So this immediate reward and the cumulative value of the next state multiplied by the discounted factor, that will give you the Q function SA. Now note that Q of SA is exactly the quantity that is maximized in the equation of optimal control policy. Now why don't we substitute this Q of SA in this entire term? Because Q of SA is the sum of immediate reward and the cumulative value of the next state. Why don't we substitute this part with Q of SA? That is what we are doing here. Optimal control policy of moving from a state S is nothing but maximizing the Q function. Simple. Instead of this lengthy representation, now we have made it more brief. The optimal control policy pi for moving from state S can be denoted as maximizing the Q function in order to move from state by taking an action A. It may at first seem surprising that one can choose globally optimal action sequences by reacting repeatedly to the local values of Q for the current state. What we are doing here is, in before case, R is not known and delta is not known. But how we are calculating both of them? By choosing globally optimal action sequences. How we are arriving at the globally optimal action sequences? By reacting repeatedly to the local values of Q. For every step, the Q value is calculated. From that, every step's Q value, the global optimal action sequence can be calculated. Where the Q value is less, that step has to be omitted. Where the Q value is more, that step have to be considered in the action sequence. That is how globally optimal action sequences can be framed. Now, this means the agent can choose the optimal action without ever conducting a look-ahead search to explicitly consider what state results from the action. So, look-ahead search is not required actually. What would be the outcome after 2-3 steps? It is not interested in. What would be the outcome or what would be the reward only in the next immediate step? That is what it is interested in. It need not search ahead of the moving sequences. It can just search with its immediate next move, immediate next state by taking this action. What would be the reward in order to learn this Q function? The part of the beauty of Q learning is that the evaluation function is defined to have precisely this particular property. The value of Q for the current state and action summarizes in a single number all the information needed to determine the discounted cumulative reward that will be gained in the future if action A is selected in state S. So what does this Q represent? Q of SA represents from this particular state, if this action is taken, what would be the cumulative reward in every step of agent from this particular state in any of the directions. That rewards, cumulative reward is taken as this Q function. Right? It adds up. It adds up all the rewards that can be accumulated when a particular action is taken to move from this state in any of the directions, any of the valid directions, legal directions. Now it will add up all those to get the cumulative reward. Now, learning the Q function corresponds to learning the optimal policy because Q function denotes the optimal sequence of actions. So the key problem is finding a reliable way to estimate training values for Q given only a sequence of immediate rewards are spread out over time. So what is the key problem here? What is the crucial problem we have to cover now is finding the most dependable way in order to estimate the training values for Q. That is to learn the Q function given only sequence of immediate rewards spread over time. Means in sequence of actions, what would be the rewards encountered? If it is given, then it is easy to learn the Q function. This can be accomplished through iterative approximation. Why we call it as iterative? In the initial stage itself, you can't say that this sequence of actions is correct and optimal in order to move the goal state. It has to iteratively refine. This step is appropriate, but this step is more appropriate. Third step is even more appropriate. So iteratively, it has to refine and approximate the sequence of actions. That is the Q function. Now to see how, notice the close relationship between Q and V star. What is V star? The value of cumulative rewards. What is Q? That is also value of cumulative rewards. So how we can represent them together? Value of cumulative rewards when moved from state S, that can be represented as maximization of the Q function for moving from state S by taking sequence of actions A dash. Okay, which allows rewriting the equation. Now this equation, what we have, Q function equation, that is sum of immediate rewards and the next state's cumulative reward value. For that we can instead of delta S of A, we can simply substitute it with Q. Because V star is similar to Q, you can simply substitute that V star with Q. So how you are writing this now? R of SA, that is immediate reward, plus the discounted factor multiplied by, instead of V star, we are using this representation now. So it is max A dash Q of, what is the next state represented as? Delta SA. When some sequence of actions are taken, the next steps are represented as delta SA. In the sequence of steps, in the sequence of actions, dash. Okay, that is how we can rewrite the equation. This recursive definition of Q provides the basis for algorithms that iteratively approximate Q, iteratively calculate, formulate the evaluation function Q. Now to describe the algorithm, we will use the symbol Q cap instead of Q. Why we use cap? I told you already. Whenever you are estimating something, whenever you are approximating something, then some error will be associated with it. So we don't say that Q is the exact value. Q is some approximation. If you want to denote that, then you take it as Q cap. Q cap denotes estimation of the Q value. Okay, so to describe the algorithm, we'll use the symbol Q cap to refer to the learner's estimate or hypothesis of the actual Q function. Okay, now in this algorithm, the learner represents its hypothesis Q cap by a large table with a separate entry for each state action pair. This is the place where your doubts have to be destroyed. I'll show you exactly how the table is maintained. For every state action pair from this particular state, say from state S1, if A1 is action A1 is taken, then what is the estimated value of Q for that S1 to move by taking an action A1? From that S1 state to move by taking an action A1. Now from S2 state, by taking an action A2, what would be the cumulative reward value? Estimated cumulative reward value that can be represented as Q cap S2 A2 and so on. Okay, so this Q cap will give the estimation of the rewards that can be accumulated by starting from state 1, by starting from state 2, by starting from state 3 and so on. Okay, so this table will provide a reference to you, to the agent, to understand from which state, if it starts, what set of values it can accumulate. And what is its motive? Always to maximize that cumulative rewards. So it will select the best move from a current state by referring to this table. So the table entry for the pair SA stores the value for Q cap SA, that is the learner's current hypothesis about the actual but unknown value Q of SA. So the actual value of Q is not known. Only the estimated value is taken. If at all it starts from this state and takes this sequence of actions, what would be the estimated reward value? That values are given in the table. Now the table can be initially filled with some random values and iteratively they can be refined. Did you understand now? Something like in back propagation algorithm to adjust the weights, you remember? In neural networks, in order to adjust the weights iteratively, you keep sending the difference in the errors. What is the prediction error? That prediction error you are back propagating so that the weights are adjusted. Again, the prediction error is checked. If the prediction error is more, again the weights are adjusted and the prediction error is checked. Now the prediction error is not more, it is just nominal. In that case, this would be the better option for weights. That is how weights are updated. Weights are initially taken as random values, but later in order to reduce the prediction error, weights are fine-tuned. In the same way, this estimation of the hypothesis, that is the Q function value, are taken with some random values. Now, see how the agent is taking the steps and in which sequence of steps the rewards accumulated is maximum. That steps rewards you have to update for Q cap S of A in the table. Again, it takes another set of steps, another sequence of actions. Now, the rewards accumulated are more than previous value. In that case, this accumulated rewards along the sequence of steps have to be updated into this table again. So iteratively, this estimation of Q function is made in order to arrive at the best estimation, which would be the maximum accumulated reward points. So the agent repeatedly observes its current state S, chooses some action A, executes this action, then observes the resulting reward. What is the resulting reward? R of SA and the new state. What is the new state? How is the new state represented? S dash, which is nothing but the change in the current state. Change is always denoted by delta. So delta S of A. What is the change by taking an action A is made in the state S, that is S dash. Okay, so it observes the resulting reward for taking that action R and also it observes the new state S dash. If it then updates the table entry for, sorry, this is Q cap. Table entry for Q cap of SA. Following each such transition, according to the rule, what is the updation rule here? You remember perceptron rule, which is used to adjust the weights. It is taken as delta W as W plus learning rate into the prediction error multiplied by the input value. In the same way, like this perceptron training rule, you will have an updation rule to update the Q value. That is nothing but how the Q value is updated. Q cap of SA, how it is updated. It is the immediate reward encountered in that particular step plus discounted value multiplied by what is the maximum accumulated reward value for moving from state S to S dash by taking an action A dash. That is given as the new value to be updated into the table, Q cap of SA. So this is the final algorithm, important algorithm. The steps are very easy to understand because you know the underlying concept. You can easily understand these steps. The Q learning algorithm starts for each S and A, that is for each state and the action to be taken to move from that state. Initialize the table entry. Initially, get the table entries Q cap of SA to 0, or you can take some random values also. It can be 0 or it can be any random value also because they will be anyway updated, okay, according to the result. That is why you just take them to be initialized with 0 or any random value. Observe the current state S, that is from which state it has to move. Do forever, continue doing it. What actions it has to do? Select an action A and execute it to move from that particular state. Now receive the immediate reward R, observe the new state S dash, new state is observed, update the table entry now. Update the table entry for Q cap of SA. How do you update? By using this update rule. This rule is called as the update rule. What does this update rule say? Q cap of SA should be modified in accordance with the new reward R given plus the discounted factor you are considering multiplied by which is the maximum cumulative value of Q in those sequence of steps taken. Among those sequence of steps taken, that Q cap S dash A dash, that is Q value, that is cumulative reward value encountered for moving to this S dash by taking action A dash. Many such steps are taken, right? Among those, which sequence of steps is the best, which will accumulate maximum reward points? That value is taken, added to the immediate reward value, and the entry in the table is updated. That is estimation of the Q function for moving from state S by taking an action A. Finally, what you have to do? Update the state S with new state S dash. Because from S dash, again it has to move to S double dash. Again it has to move to S triple dash. Right? So each time the new state should replace the existing state so that it carries on. It performs this entire steps of sequence of steps again on the next state in order to learn the evaluation function Q. Got it, students? What we are trying to learn from Q function? It helps us to evaluate what steps can be taken. It helps us to design the optimal control policy by helping us with the evaluation function Q. In the next class, we'll understand this more better with an illustrative example and how this will converge to a particular value, because this is infinitely being done. And when it should stop? Only when the values further doesn't change. It has to converge to a particular value. It has to stay stable at a particular value. That is called as the point of convergence. How it reaches there, we'll see with the convergence theorem in the next class. Yeah, I have taken too much time just to complete the topic, otherwise the continuity will be lost. And many of you are patiently staying back in the class. That is very good. Any doubts in today's class, students?
No, ma'am.
Concepts are little complex. You just see the videos repeatedly. You'll surely understand. Okay? We'll meet in the next class.